Okay, we are going to continue our discussion of counting and probability with the pigeonhole principle. The pigeonhole principle states that if n pigeons fly into m pigeonholes and n is greater than m, then at least one hole must contain 2 or more pigeons. This is shown with the example of n equals 5 and m equals 4. So at least two pigeons have to be in one of the pigeonholes. Illustration A shows the pigeons perched next to their holes, and B shows the correspondence from pigeons to pigeonholes. Pigeonhole principle is sometimes called the Dirichlet box principle because it was first stated by Dirichlet. I don't know how to pronounce that. I don't know why I'm trying. Anyway, the pigeonhole principle formalized is a function from one finite set to a smaller finite set cannot be one-to-one. There must be at least 2 elements in the domain that have the same image in the codomain. In a group of 6 people, must there be at least 2 who are born in the same month? In a group of 13 people, must there be at least 2 who are born in the same month? In a group of 6 people, must there be at least 2 who were born in the same month? Yeah, because there's less than 12 people, and there's 12 months. So, but of a group of 13? Yeah, because there's only 12 months. So, among the residents of New York City, must there be at least 2 people with the same number of hairs on their heads? You got to know a few things about people in New York City to answer that one. True. So we went through the A, and they do a little diagram to show that from 13 people to 12 months is not one-to-one. B, the answer is yes. In this example, the pigeons are the people of New York City, and the pigeonholes are all the possible numbers of hairs on any individual's head. Call the population of New York City P, and it is known that P is at least 8 million people. Also, the maximum number of hairs on any person's head is known to be less than 300,000. Okay, so define a function of h from the set of people in New York City to the set 0 to 300,000, and show it in the arrow diagram. Since the number of people in New York City is larger than the number of possible pairs of hairs on their heads, the function h is not one-to-one. At least 2 arrows point to the same number. And this means that at least 2 people have the same number of hairs on their heads. So, application to decimal expansions of fractions. One important consequence of the pigeonhole principle is the fact that decimal expansion of any rational number either terminates or repeats. A terminating decimal is one like 3.625, and a repeating decimal is one like 2.38246 with a bar over the 2, 4, and 6, where the bar over the digits means that these digits are repeated forever. Let a and b be integers, and consider the fraction a over b. where for simplicity A and B are both assumed to be positive. The decimal expansion of A divided by B is obtained by dividing A by B, as illustrated here for A equals 3 and B equals 14. So you divide and you get a decimal number. Let R, O, equal A, and let R 1, 2, 3, etc. be the successive remainders obtained from the long division of A by B. By the quotient remainder theorem, each remainder must be between 0 and B minus 1. If some remainder Ri equals 0, then the division terminates and A and B has a terminating decimal expansion. If no Ri equals 0, then the division process and hence the sequence of remainders continues forever. By the pigeonhole principle, since there are more remainders than values that the remainders can take, some remainder value must repeat Rj equals Rk for some indices j and k, with j less than k. This is illustrated here for A equals 3 and B equals 14. So it follows that the decimal digits obtained from the divisions between Rj and Rk minus 1 repeat forever. In the case of 3 over 14, the repetition begins at R7 equals 2 equals Ri. And the decimal expansion repeats the quotients obtained from the division of R1 through R6 forever. The generalized pigeonhole principle. A generalization of the pigeonhole principle states that if n pigeons fly into m pigeonholes, and for some positive integer k, km is less than n, then at least one pigeonhole contains k plus 1 or more pigeons. So this figure shows m equals 4, n equals 9, and k equals 2. Since 2 times 4 is less than 9, at least one pigeonhole contains 3, 2 plus 1, or more pigeons. So any function f from a finite set x with n elements to a finite set y with m elements, and for any positive integer k, if km is less than n, then there is some y, which is an element of big Y, such that y is the image of at least k plus 1 distinct elements of x. So you can tell how many are going to be in the each hole by figuring out k. Show how the generalized pigeonhole principle implies that a group of 85 people, at least 4 must have the same last initial. So in this example, pigeons are the 85 people, and the pigeonholes are the 26 possible last initials of their names. Consider the function L from people to initials defined by the following arrow diagram. X1 to X85 and 1 through 26, or A through Z. So since 3 times 26 is 78, and which is less than 85, The generalized pigeonhole principle states that some initial must be the image of at least 4 or 3 plus 1 people. Thus, at least 4 people have the same last initial. Consider the following contrapositive form of the generalized pigeonhole principle. For any function f from a finite set x with n elements to a finite set y with m elements, and for any positive integer k, if for each element, little y element of big Y, the inverse function of y has at most k elements, then x has at most k times m elements. In other words, n is less than or equal to km. And proof of the pigeonhole principle. Well, the truth of the pigeonhole principle depends essentially on the sets involved being finite. We know that a set is called finite if and only if it is the empty set or there is a one-to-one correspondence from 1, 2, 3 to n to it, where n is a positive integer. In the first case, the number of elements in the set is said to be 0. In the second case, it is said to be n. A set that is not finite is called infinite. Thus, any finite set is either empty or can be written in the form of x1, x2, x3, etc. to xn, where n is a positive integer. So the theorem 941, the pigeonhole principle, is for any function f from a finite set x with n elements to a finite set y with m elements. If n is greater than m, then f is not one-to-one. An important theorem that follows from the pigeonhole principle states that a function from one finite set to another finite set of the same size is one-to-one if and only if it is onto. The result does not hold for infinite sets. Let x and y be finite sets with the same number of elements, and suppose f is a function from x to y, then f is one-to-one if and only if f is onto. So that'd be it for that little side deck. We're only going to cover 2 today. Let's see. It was 4. Yeah. All right. All right. So, counting and probability, section 5. Counting subsets of a set. Combinations. All right. The number of subsets of size R that can be chosen from S equals the number of subsets of size R that S has. Each individual subset of size R is called an R combination of the set. Let n and R be non-negative integers with R less than or equal to n. An R combination of a set of n elements is a subset of R if of the n elements. The symbol n over R in parentheses without a bar like division reads n choose R. Denotes the number of subsets of size R or R combinations that can be formed from a set of n elements. Consider a set consisting of 4 people: Ann, Bob, Sid, and Dan. Given the set, each subset of size 3 is a 3 combination of its elements. List all the 3 combinations of the set. Use that result to find 4, choose 3. In how many ways can the people in the set form a committee of size 3? Each combination, 3 combination, can be obtained by leaving out one of the elements of the set. There are 4 elements in the set of 3 combinations in part A, so there are 4 combinations of 3 for each out of the set of 4. The number of ways people in the set can form a committee of size 3 is the number of distinct such committees, which is the same as the number of subsets of size 3 and equals the number of 3 combinations of elements in the set. Thus, there are 4 ways the people in the set can form a committee of size 3. There are 2 distinct methods that can be used to select R, objects from a set of n elements. In an ordered selection, it is not only what elements are chosen, but also the order in which they are chosen that matters. 2 ordered selections are said to be the same if the elements chosen are the same, and also if the elements are chosen in the same order. An ordered selection of R elements from a set of n elements is a R permutation of the set. In an unordered selection, on the other hand, it is only the identity of the chosen elements that matters. 2 unordered selections are said to be the same if they consist of the same elements, regardless of the order in which the elements are chosen. An unordered selection of R elements from a set of n elements is the same as a subset of size R or an R combination of the set. How many unordered selections of 2 elements can be made from the set 0, 1, 2, 3? How many unordered selections? I'm going to guess it's going to be 12, because you have 4 possibilities for the first selection, 3 possibilities for the second selection. Does that make sense? An unordered selection of 2 elements is the same as 2 combination, or a subset of size 2, taken from the set. They can be listed systematically. Oh, it's divided by 2, yeah. It would be 6, okay. Since this listing exhausts all possibilities, there are 6 subsets in all, which is the number of unordered selections of 2 elements from a set of 4. When the values of n and r are small, it is reasonable to calculate values of n choose r using the method of complete enumeration. But when n and r are large, it is not feasible to compute these numbers by listing and counting all the possibilities. The general values of n choose r can be found by a somewhat indirect but simple method. An equation is derived that contains n choose r as a factor. Then the equation is solved to obtain a formula for n choose r. Write all 2 permutations of the set 0, 1, 2, 3. Find an equation relating the number of 2 permutations and the number of 2 combinations for choose r, or for r choose 2, and solve this equation for 4 choose 2. According to theorem 923, the number of 2 permutations of the set 0, 1, 2, 3 is p of 2, 4, and 2, which equals 12. That's what I calculated on the previous example. If n and r are integers, just a review of theorem 923, if n and r are integers and 1 is less than or equal to r, which is less than or equal to n, then the number of r permutations of a set of n elements is given by the formula p of n and r equals n factorial over n minus r factorial. Now the act of constructing a 2 permutation of the set can be thought of as a 2-step process. Choose a subset of 2 elements from the set, and then choose an ordering for the 2-set element subset. So this process is illustrated by the possibility tree shown here. You can get 12 combinations. The number of ways to perform step 1 is 4 choose 2 is the same as the number of subsets of size 2 that can be chosen from the set. And the number of ways to perform step 2 is is that 2 factorial? The number of ways to order the elements of a set of size 2? Because the number of ways of performing the whole process is a number of 2 permutations of the set, which equals p of 4 and 2. It follows from the product rule that p of 4 times 4 and 2 equals 4 choose 2 times the 2 factorial. So solving the equation for 4 choose 2 equals p of 4 p of 4 and 2 equals 4 factorial over 4 minus 2 factorial. So substituting yields 4 choose 2 equals 4 factorial over 2 factorial times 4 minus 2 factorial. So the computational formula for n choose r, the number of subsets of size r that can be chosen from a set of n elements, is given by the formula p of n and r over r factorial, or equivalently n factorial over r factorial times n minus r factorial, where n and r are non-negative integers with r less than or equal to n. Consider the problem of choosing 5 members of a group of 12 to work as a team on a special project. How many different 5-person teams can be chosen? Now, the number of distinct 5-person teams is the same as the number of subsets of size 5, or 5 combinations, that can be chosen from a set of 12. This number is 12 choose 5. By theorem 951, that equals 12 factorial over 5 factorial times 12 minus 5 factorial. So it multiplies out and all that sort of stuff to be 792 distinct 5-person teams. Use the multiplication rule to show that k of m and n, or k sub m and n, is a complete bipartite graph on m and n vertices, has m times n edges. Use 2 combinations to show that k of n is a complete graph on n vertices, has n times n minus 1 over 2 edges. Now, a complete bipartite graph on M and N vertices is a simple graph whose vertices can be divided into two distinct non-overlapping sets, say V with M vertices and W with N vertices, in such a way that there is exactly one edge from each vertex of V to each vertex of W. There is no edge from any one vertex of V to any other vertex of V, and there's no edge from any one vertex of W to any other vertex of W. Label M vertices of V as V sub 1, V sub 2, etc. to V sub N, or M. Think of constructing the edges between the vertices of V and the vertices of W as an M-step process. For each integer k from 1 through M, draw exactly one edge from V sub k to each of the n edges of W. Because each step can be performed in n ways and there are m steps, by the multiplication rule, there are m times n ways to construct all the edges. Thus, k sub m and n has m times n edges. A complete graph on n vertices is a simple graph with n vertices and exactly one edge between each pair of vertices. If n is equal to 1, then k has one vertex and 0 edges. And since n times n over 1, or times n minus 1 all over 2 equals 0 for n equals 1, then k sub n has n times n minus 1 over 2 edges. If n is greater than or equal to 2, then since any two distinct vertices of k are connected by exactly one edge, there are as many edges in K as there are subsets of size 2 in the set of n vertices. By theorem 951, there are n choose 2 such sets, and you do that and substitute it into substitute n and 2 into theorem 951, and you get n times n minus 1 all over 2 edges for K. A game of poker is played with an ordinary deck of 52 cards. Various 5-card holdings are given special names, and certain holdings beat certain other holdings. The named holdings are listed from highest to lowest below. Royal flush, straight flush, 4 of a kind, full house, flush, straight, 3 of a kind, 2 pair, 1 pair, no pairs. So how many 5-card poker hands contain 2 pairs? If a 5-card hand is dealt at random from an ordinary deck of cards, what is the probability that the hand contains 2 pairs? Consider forming a hand with 2 pairs as a 4-step process. Choose 2 denominations for the pairs. Choose 2 cards from the smaller denomination. Choose 2 cards from the larger denomination, and then choose 1 card from those remaining. The number of ways to perform step 1 is 13 choose 2, because there are 13 denominations in all. The number of ways to perform each of steps 2 and 3 is 4 choose 2, because there are 4 cards from each denomination, 1 in each suit. The number of ways to perform step 4 is 44 choose 1, because the fifth card is chosen from the 11 denominations not included in the pair, and there are 4 cards of each denomination. So the total number of hands with 2 pairs is 13 choose 2 times 4 choose 2 times 4 choose 2 times 44 choose 1, which equals a little over 123,000 possible hands. Now the total number of 5-card hands from an ordinary deck of cards is 52 choose 5, or almost 2.6 million. Thus, if all hands are equally likely, the probability of obtaining a hand with 2 pairs is roughly 4.75%. A little statistic thing that I read somewhere. It is more likely for you to die in your next car ride, statistically, than it is for you to get a royal flush dealt to you in a hand of poker. A little scary, or a little disturbing at how rare a royal flush is. I had the pleasure of getting a royal flush in Vegas one time, but obviously I haven't died in my next car ride yet. Who knows? Today is a gift. Tomorrow is not guaranteed. Anyway, consider the various ways of ordering the letters in the word Mississippi. How many distinguishable orderings are there? Well, this example generalizes example 9510. Imagine placing the 11 letters of Mississippi one after another into 11 positions. Because copies of the same letter cannot be distinguished from one another, once the positions for a certain letter are known, then all copies of the letter can go into the positions in any order. It follows that constructing and ordering for the letters can be thought of as a 4-step process. Choose a subset of 4 positions for the S's. Choose a subset for the 4 positions for the I's. Choose a subset of the 2 positions for the P's, and choose a subset of 1 position for the M. Since there are 11 positions in all, there are 11 choose 4 subsets for the positions for the S's. Since the 4 S's are in place, there are 7 positions that remain empty, so there are 7 choose 4 subsets of 4 positions for the I's. After the I's are in place, there are 3 positions left empty, so there are 3 choose 2 subsets of 2 positions for the P's, and that leaves just 1 position for the M, but 1 equals 1 choose 1. So hence, by the multiplication rule, the number of ways to position all the letters is 11 choose 4 times 7 choose 4 times 3 choose 2 times 1 choose 1, which multiplies out to be 34,650. So quite a few different combinations, or permutations, I should say. Permutations with sets of indistinguishable objects. Suppose a collection consists of n objects, of which n1 are of type 1 and indistinguishable from each other. N2 are of type 2 and are indistinguishable from each other. All the way up to n sub k are of type k and are indistinguishable from each other. And suppose that n plus 1 plus 2 plus 3, etc. to n sub k equals n. Then the number of distinguishable permutations of the n objects is n choose n1, n1 or n minus n1, choose n2. N minus n1 minus n2, choose n3, etc., which is equal to n factorial over n1 factorial times n2 factorial times n3 factorial, etc., to times n sub k factorial. Some advice about counting. A group consists of 5 men and 7 women. How many teams of 5 can contain at least 1 man? The incorrect solution. Imagine constructing the team as a 2-step process. Choose a subset of 1 man from 5 men. Choose a subset of 4 others from the remaining 11 people. Hence, by the multiplication rule, there are 1,650 5-person teams that contain at least 1 man. Analysis of the incorrect solution. The problem with the solution above is that some teams are counted more than once. So suppose the men are Anwar, Ben, Carlos, Dwayne, and Ed, and the women are Fumiko, Gail, Huifan, Inez, Jill, Kim, and Laura. According to the method described previously, one possible outcome of the 2-step process is as follows. Step 1, choose Anwar. Outcome of step 2, choose Ben, Gail, Inez, and Jill. In this case, the team would be Anwar, Ben, Gail, Inez, and Jill. But another possible outcome is outcome of step 1 is Ben. Outcome of step 2 is Anwar, Gail, Inez, and Jill, which also gives the team given before. Thus, this one team is given by 2 different branches of the possibility tree. So it is counted twice. So it is an incorrect method, process of counting. Now, here's a question. See if you take up the challenge. See if you can count up. I saw a sign in a Waffle House one day saying that there are so many different ways to have their hash browns. Because you can add the onions and the cheese and all that sort of fun stuff. Tomatoes, mushrooms, all these different toppings. When I took this class, I and found out how to count large numbers like that. I went ahead and counted up how many combinations you could have of Waffle House hash browns. The number was larger than the one on the sign. So I'll call it extra credit. I'll give you 10 bonus points on the final if you can show. If you go to Waffle House, look at their menu, and can calculate the number of ways and show your work and explain why you came up with this number, the number of ways you can have Waffle House hash browns. So 10 points on your final if you do the counting right and come up with the correct number. The number I counted up is no longer valid because it's they changed their menu and added some toppings, so the number's now much larger. But yeah, a little extra credit for you. So, but yeah. But that'll be it for the day. We're kind of ahead of the game. We might take a day off next week and kind of we only have 4 sections left and 4 class sessions left. So, and we usually cover 2 or 3 per day. So we have a couple of extra days. So we might take some days off next week or the following week. But anyway, have a good day. See you on Tuesday. Have a good weekend.